This mirror is concave mirror. Okay, what we are going to do is like a mirror formula. What is the use of mirrors formula like? So it will help us to predict the position of image. Means if you know object, if you know the position of object, you can predict the position of the image with the help of this formula. There are two things are there. We can take help of geometrical instruments. We can predict the position of image. Then using directly the formula, we can predict here. Okay, for this I'll take help of this particular thing. So here an object O is kept beyond C, and the image will be formed between F and C. So there's an incident ray. So the ray will propagate here, get reflected by mirror, and will meet the principal axis at I. Similarly, the incident ray will go and strike the lower part of the mirror. After reflection will come and meet the principal axis at this point. So look at the reflected rays, they are converging. So therefore this should be a real image. Look at the object, these are incident rays. They are diverging from a point. So this should be the real object. So for a real object, what we're getting is a real image. Later I'll come in detail. Just only we are going to discuss now the mirror formula. These are incident rays. This is reflected ray. I think same thing applicable here also. This is incident ray. And the other one is the reflected ray. Okay, now we'll define all the distances from the pole. Let me take some color. Yeah. This will be the focal length. This will be the image distance. This will be the center of radius of curvature, and this will be the object distance. This will be the focus, focal length. This will be the image distance, will denote by V. Radius of curvature. This will be the object distance U. All the distances I should measure from the pole. And the incident rays are moving towards left. So any distances measured in the direction of incident ray should be taken as positive. So what is the sign convention? So what sign convention says? Distances measured in the direction of must be taken as positive. Okay, fine. This is okay. The distances measured in the direction of incident ray must be positive, and all the distances are measured from the pole. Okay, these are the pole, that one. Okay, let's come forward. Okay, if you look at this whole setup, I'll be using, say, I'll be saying that some triangle. So let's make things a little bit simplified rather than fighting with this one. This whole mirror we can just replace with a one straight line for mathematical convenience. It is. Don't really, nothing will happen of this kind practically, just for our mathematical convenient. Okay, this is the center of curvature. This will be the normal, no? Let's trace out the ray. The ray after reflection, and next the other ray. This is incident ray. After reflection, it will meet at point, this one. So you can, sir, where is the mirror? This is for mathematical convenient. This is purely a mathematical convenient. So this will be beta, this will be gamma, this will be alpha. Real object, a real image will be formed. Okay, there is no such thing like, sir, where mirror gone? Just like a, for mathematical convenience, we can show the reflection with respect to vertical line. Just for namesake, you can show the mirror. So the reflections, everything with respect to vertical, you can show, and you'll get a well-defined geometrical shapes so that you can write equations very easily. There's a methodology what we are going to follow here. Okay, let's do one thing. Okay, what is the angle of incidence? Looking at this, theta. So the angle of reflection will also be theta. Then, okay, let's get into the triangle. Triangle CMO. In the triangle CMO, alpha, gamma should be equal to alpha plus theta. So first of all, what are alpha, beta, gamma? What is theta? Theta here, angle of incidence should be equal to angle of reflection. And this will be a normal. This will become a normal. Then, so what are alpha, beta? Angle made by the incident ray with the principal axis. This is the principal axis. Angle made by the incident ray with the principal axis is what? Alpha. What is beta? Angle made by the reflected ray with the principal axis is beta. What is gamma? Angle made by the normal with the principal axis will become gamma. Okay, fine. So now look at this triangle CMO. This theta and alpha will become interior angle, gamma will become exterior angle. So the exterior angle should be equal to sum of interior angle. So theta plus alpha. Similarly, look at this triangle high MC. Triangle high MC. So beta should be equal to gamma plus theta. This angle beta, look at this triangle IMC. Beta should be equal to gamma plus theta. Okay, this and what are the rays? The rays are paraxial later on. So what all we discuss is for paraxial rays only. So small angles we can write theta sin theta. Theta will become tan theta based on our conditions. Okay, let's simplify this one. Like a gamma beta equal to gamma plus substituting. Okay, the gamma equal to alpha plus theta, I can write it as beta minus gamma. So 2 gamma equal to alpha plus beta. For paraxial rays, so what we can write it as like a gamma will become 2 tan gamma. Alpha will become tan alpha. This will become tan beta. Okay, from the triangle, what is tan gamma? Here, look at this triangle. So it should be PM by PC. So from triangle, so what we can write it as PM by PC. Similarly, tan alpha, look at this triangle, tan alpha, OPM. In the triangle OPM, or I'll write for your convenient why to trouble you. Tan alpha triangle PMI. Tan alpha equal to PM by PI. sorry. PMI, no? So tan beta it is, sorry. Similarly, triangle PMC. Tan gamma equal to PM by PC. Similarly, in the triangle PMO, tan alpha should be equal to PM by PO. So those things I'm going to replace it here. So what is tan alpha? Will be PM by PO. tan beta PM by PR. Okay, the PM gets eliminated. So 2 by PC equal to 1 by PO plus 1 by PR. What is PC? PC should be equal to the radius of curvature. Here come for this one. Let's look at the left corner here. So what is the distance PC? Distance PC is what we indicated by R, no? Radius of curvature. What is the distance PF? Should be equal to F focal length. What is PI? PI should be equal to image distance V. And what is PO? Object distance U. U is what? Object distance. What is V? Image distance. So these are the symbols. Let me define them. This is the first time, no? Okay, let me clearly give all the information. What is F? F will be focal length. What about R? R is called as radius of curvature. Okay, now what is the convention says? The distances measured in the direction of incident ray should be positive. So how I'm going to measure? I'm going to measure opposite incident ray. So therefore, what is PC? PC, what we can write it as? PC should be equal to minus R. PC should be equal to minus R. PO equal to minus U minus V. What is F is equal to? R by 2. Yesterday, previous class we have derived, no? So in place of R by 2, what we can write as? 1 by F. So solving this, finally I'll end up with, this is our mirror formula. You can write it in various forms. F is equal to UV by U plus V, where substitute U, V, substitute unknown, substitute known with sign. Again, you have to substitute here. Okay, look at this signs. I think this will be really very important. From based on the diagram, I replaced here. So we know F equal to R by 2. In place of R by 2, I can write it as focal length. So there's a mirror formula. What is the use of this? See, there are two ways to predict the position of image. One, geometrical instrument. Other one, this mirror formula. With the help of mirror formula, so what I can do is like directly, I know the position, I know focal length of a mirror. Then I'll keep the object. I know where object is kept. I'll get the position of image. I need not to go for the geometrical instrument with the help of this formula. With the help of this formula, I can do. So if you know object distance and focal length of mirror, the unknown thing you can find out. Okay, let me solve for V. So it will be 1 by F. So what is the expression for V will be? V will be F U by U minus F. So substitute U and F with sign. The sign of V we have to interpret here. So if you know object distance and the focal length of mirror, you can predict the image distance. Able to make it out? So this is about the what we derived. We derived this for concave mirror, no? Is it applicable for convex mirror? Yes, it is applicable for both. What all the formula is there? Mirror formula. Applicable for concave and convex mirrors. It's not that since we derived for concave, will it be applicable for concave? It's a generalized one. It is in fact applicable for any spherical mirror. Any spherical means concave convex mirror here. Okay, the year of thought. So drawing ray diagram, no, so this will really help us. So practically it should be that one. Say M will be very close to P. Already we defined paraxial, and the angle of incidence, this will be very small, theta will be very small. So we can treat these are paraxial. For paraxial rays, we can do these approximations. Alpha, I can write it as tan alpha. So like alpha, tan alpha, gamma, tan gamma, beta, tan gamma, only for paraxial rays. Okay, so this is about the mirror formula, very, very important. Almost every numerical, I'll be taking help of this one. Okay, now, what about the focal length for concave and convex mirror? So I have here, this is the, what is the mirror? This is a concave mirror. This is a convex mirror. The direction of incident ray should be taken positive. So this is the direction of incident ray. These are incident rays. And similarly here, these are incident rays. No, if object at infinity, I'm going to take help of this formula. Object at infinity, where the image will be. If put u equal to infinity, where object will, what happen will be at infinity here. What if the image will be at the focus? So then we'll define the focal length. So how we measure focal length? Opposite to incident ray, because the incident rays are towards left, and we are measuring the focal length from the pole opposite incident ray. So therefore, for concave mirror, what is the focal length? Will be negative. Focal length for concave mirror will be negative. Like we write f equal to -10, -20, -30, or depend upon the curvature of that one. Similarly, for convex mirror, we'll see that these are direction of incident rays. After reflection, the rays should diverge from a point where the image will be located at the focus. Put u equal to infinity, put u equal to infinity. I'll get v equal to f here. So where the image will be at the focus. How I measure the focal length now in the direction of incident ray? So what is the focal length for convex mirror? Focal length for convex mirror, it will be positive. Focal length for this is very important now. So when we are doing any problems, no,